Now we're going to go through enzymes. Some characteristics that you want to remember about all enzymes is that they are made of protein and they're catalysts, but they're special catalysts because they're found solely in living things. So always remember that enzymes are catalysts, but they are found in living things. They speed up the rate of chemical reactions, which lowers the activation energy. And the great thing about enzymes is they're reusable. They only look for the substrate that's for them. So there's only one specific substrate for the enzyme. As you see here, we have the substrate and the enzyme. And this particular substrate fits perfectly like a puzzle piece into that enzyme, right in there. Now, one trick that may help you is that enzymes, a lot of times they end in ASE, so that's a clue. And they can do a couple of things. They can synthesize, which means put things together, that's anabolism, or they can metabolize, break things apart into smaller pieces, which is catabolism. The enzyme substrate complex fits like a lock and key. So just like your house key fits into the lock all of the time and you can reuse it over and over and over again, same thing with the enzyme and the substrate. So the substrate fits into the active site of the enzyme. Once it binds to the active site, then the products are formed. In this diagram, it's catabolism because it's breaking the beginning substrate into two smaller pieces. Some factors that affect enzymes are pH and temperature. Let's start with pH. If the pH is too high or too low, that'll decrease enzyme rate. The best pH, which is what optimal means, that will vary depending on where the enzyme is located. So if you look at the graph pictured here, you can see the pH is on the x-axis and the relative rate of activity is on the y-axis. So that's what we're measuring. We're measuring what's on the y-axis and we're testing what's on the x-axis. Well, gastric protease is the dotted line, and as you see, protease, ending in ASE, lets you know it's an enzyme found in the stomach. Intestinal protease, ASE, it's an enzyme found in the intestines. So if we look at the graph of both, let's see which one has the optimal pH. So the best pH for gastric protease, well, that would be at this peak up here, and we get somewhere about 3 for the optimal pH. How about intestinal protease? That would be the optimal location, and if we come down, we can see that that's about 9 for intestinal protease. Some other factors would be temperature, as I mentioned before. If it's too hot, then the enzyme will denature, meaning it'll break apart. If it's too cold, they're not very active. They don't like that either. So looking at this graph, what temperature would be most effective for this enzyme? Again, we can go to the peak of our graph, and we kind of come down, gives us an idea that it's around 38 degrees Celsius. Finally, try to identify the enzyme, the substrate, the enzyme-substrate complex, and the products. As you look at those, hopefully when you identify the enzyme, remember the substrate will fit into the enzyme's active site. So I can see that letter D is the enzyme. In here, This is the active site. Well, if that's the active site, the substrate has to fit in there. So A must be the substrate. The enzyme substrate complex is when they're connected, and that's B. And finally, the products is what would be formed, or are what would be formed, and letter C happens to be the products. Since we started here with a large substrate and we have two smaller pieces, this is an example of catabolism because the large substrate was broken into two smaller pieces.